Hi everyone, I'm Ted Pyne, and today I'm going to be talking about pseudodistributions that beat all pseudorandom generators. And this is joint work with Cyril Vadan. To derandomize a computational model, one standard approach is to create a pseudorandom generator. Here, we call G, a function from S bits of seed to N bits of output, an epsilon PRG for a class of functions on N bits to 1 bit, if for all B in the class, the expectation of B under the uniform distribution is within epsilon of its expectation under a uniformly random output of the PRG. In 2018, Braverman, Cohen, and Garg introduced a relaxation of PRGs called pseudorandom pseudodistribution generators, or weighted PRGs. The weighted PRG notation was introduced by Cohen et al. In this conference, and we choose to adopt it. Here, rather than saying that G is a PRG, we say that a tuple of functions, G rho, define an epsilon weighted PRG if G is a function from the S bit seed to N bits of output, and rho is a function from the S bits of seed to the reals. We say that it's an epsilon weighted PRG if rather than the expectation of B over a random output of G being close to the true expectation of B, the weighted expectation, where we evaluate B on a certain output of G and then multiply by the weight of this output, where the weight is specified by this function rho. If this expectation is close to the true expectation, we say that it's an epsilon weighted PRG. So, some comments. A PRG is a weighted PRG with the weight function rho identically 1. These suffice for two-sided derandomization because we can estimate the acceptance probability of any function in the class. And finally, if G rho is an epsilon weighted PRG, then G is an epsilon hitting set generator. And it's also worth noting that this function rho can be unboundedly positive and it can be negative. And in fact, any weighted PRG can be written as the difference of two PRGs multiplied by positive coefficients. For the model of ordered branching programs, which we haven't introduced yet, but just for now, let's consider them parameterized by their length, n, and their width, w. The optimal PRG, obtained via the probabilistic method, has seed length order log nw over epsilon. In 1992, Nissan, and in 1994, Impagliazzo, Nissan, Vigderson, constructed epsilon PRGs for the model with seed length log n times log nw over epsilon, so a factor of log n away from optimal. In 2018, Braverman, Cohen, and Garg constructed a weighted PRG with improved dependence on epsilon. Here we can see that there's a slight degradation, some log-log factors, in the dependence on the log n, log nw term, but we obtain nearly optimal dependence on the error parameter, an additive plus log 1 over epsilon, up to some log-log factors. And in 2020, Chattopadhyay and Liao improved this to an optimal dependence on epsilon, with again some degradation of log-log factors in the other terms. Our main result is an explicit weighted PRG that is better than any PRG with respect to a concrete computational model. Formally, there's an epsilon weighted PRG for permutation branching programs of unbounded width with a single accept vertex that has seed length O tilde log n square root log n over epsilon plus log 1 over epsilon. Here, if we take epsilon to be inverse polynomial in n, we obtain seed length roughly log to the 3 halves n. Prior work of Hosa, Pyne, and Vadan has established that any epsilon PRG for this model has seed length omega log n log 1 over epsilon. And so here, if we take epsilon to be inverse polynomially small in n, we obtain a seed length lower bound of log squared n for any, for instance, 1 over n PRG for the model. So here we obtain roughly a square root log n gap between an explicit weighted PRG and any PRG. Now we'll introduce some of the models under consideration. The first one we introduce is ordered branching programs of width w and length n. And this model captures how a small space algorithm accesses its random bits. We start at the start state in layer 1, and then we read the first bit, x1. If the bit we read corresponds to a 1, we transition along the 1 edge to this state, And if the bit we read is a 0, we transition along the 0 edge to this state. And we update in this way, first reading x1, then x2, continuing on, until the final layer, where if we reach a vertex marked as accept, we say that the branching program accepts and returns 1, and otherwise we say that the program rejects and returns 0. Here we just have a quick example of a branching program being evaluated on an input, where we have following the transition for 0, followed by 1, followed by 1, and because we do not reach an accept vertex, we say that the program returns 0. Permutation branching programs are a well-studied subset of ordered branching programs that require that each input bit defines a permutation on the states. So here we can see that the 1 transitions from layer 0 to layer 1 have the form where they form a permutation on the states 1 through 3. This is also true for layer 2 and for layer 3. There's been extensive work for pseudorandom generators for this more restricted model. So first, Nissan and INW, which hold for general order branching programs, still achieve seed length log n times log nw over epsilon. In addition, prior work has established optimal PRGs for the constant width, constant error case here. And prior work for the regular case has managed to, which includes permutation branching programs, has managed to obtain nearly optimal dependence on n versus the Nissan and INW generators. And finally, recent work gives a PRG for unbounded width permutation branching programs with a single accept vertex with seed length log n plus log 1 over epsilon. So here we can see that there's no dependence on the width, w, but we restrict to a single accept vertex. And this is not true for prior work. Unfortunately, for the parameter regime motivated by the derandomization of space-bounded computation, that is polynomial width and an arbitrary set of accept vertices, the best known PRG remains the 1992 result of Nissan. Now we'll recall our main result before discussing some implications. First, by taking epsilon to dividing by the number of accept vertices in the main theorem, effectively, we obtain that there exists an explicit epsilon-weighted PRG for permutation branching programs of width w with an arbitrary set of accept vertices, with seed length effectively where we had a 1 over epsilon term, we now have a w over epsilon term. This breaks the log squared n seed length barrier of Nissan, even for polynomial width and inverse polynomial error. And in fact, there was no previous weighted PRG, or PRG, with seed length little o of log squared n, even for width 3 and inverse polynomial error, or polynomial width and constant error. We also obtain a result for ordered branching programs of a similar form as prior ones of Braverman, Cohen, and Garg, and Chattopadhyay and Liao. We obtain a seed length of log n times log nw plus o tilde log 1 over epsilon. This was independently discovered by Cohen, Duran, Radard, Sperlo, and Tashma, and appears in the same conference. And in fact, this result was subsequently improved by Hosa, who eliminated the final log-log factor. We're going to begin by outlining the proof of this result, then detailing where the permutation case differs. At a high level, our weighted PRG is based on interpreting the space-efficient algorithm for estimating random walk probabilities of Ahmadinejad, Kellner, Murtaugh, Peebles, Sidvert, and Vadan as a weighted PRG with large seed length. We then use methods of Hosa, Pyne, Vadan to derandomize. In order to introduce this, we're going to view branching programs as directed graphs. So here, let's let B sub I be the ith layer of the branching program. And we can view this as a layered graph where we have the states at layer I and the states at layer I plus 1, and then transitions given by these edges. And we can consider the random walk matrix of this layer, where with probability 1/2, we transition along the gray edge, and with probability 1/2, we transition along the red. And from this, we can obtain the random walk matrix corresponding to this transition. Furthermore, we can define products of these, where we take the products of the transitions from layer I to layer j, and note that this corresponds to truly random walks of length j minus I over the branching program. What this means is truly random walks correspond to the input to the branching program being the uniform distribution. With these random walks on layers, we can define the random walk matrix of the entire branching program as the block matrix, where block I, I plus 1 corresponds to the transition from layer I to layer I plus 1. And here, note that we've forgotten information about the labels of this branching program, and we're simply viewing it as a directed graph. Now that we're viewing it as a directed graph, we can use tools from spectral graph theory. We can define the Laplacian of the branching program as simply the identity matrix with the correct dimensions minus the random walk matrix. One natural question is, why is the Laplacian of a branching program interesting or useful? The key observation behind this result, and the reason the Laplacian is interesting, is that the inverse of the Laplacian sums up walks over this directed graph of all lengths. Here, because the directed graph has no edges from layer n back to layer 1, we see that walks on this graph have a particular form where we have walks of length 1 up to length n. And in particular, if we look at the 0nth block of this matrix, we see that it contains random walks from the initial layer to the final layer, which correspond to transition probabilities over truly random input over the branching program. What this means is an accurate estimate of L inverse implies an accurate estimate of random walks over the branching program. Now suppose we have a weak estimate, L inverse tilde of L inverse, that we want to convert to a strong estimate. Formally, we measure this by comparing L inverse tilde to the true inverse in the following form. We take L inverse tilde times L and compare it to the identity matrix. Note that if L inverse tilde is the inverse exactly, this has norm 0. But suppose it has norm less than alpha, less than 1 for some submultiplicative matrix norm. Then we can write the difference between L inverse tilde and L inverse as a power series, as a matrix power series. And by taking the first m terms, note that this is preconditioned Richardson iteration, which is a very standard result, we obtain that this L inverse m tilde, corresponding to the first m terms of the power series, with respect to this notion of approximation, is an alpha to the m plus 1 approximation, which, as we can see, since alpha is less than 1, is converging exponentially with m. And just a note that we can pass from this notion of approximation to a conventional notion, say of entry-wise distance, at a cost of poly nw. And in fact, in order to remove the factor of w here, which we need for our results that are independent of width, we instead consider the Laplacian defined by the identity minus some small subunit scaling factor applied to w. Now that we know that we can boost a weak estimate, L inverse tilde, if we have that this error term has norm less than alpha less than 1 with respect to some norm, our goal is to construct this weak estimate. To do so, we replace truly random input with the output of a PRG, where bi to j tilde consists of the transition probabilities from layer I to layer j under the Nissan generator with error delta 1 over poly nw. So formally, we had transition probabilities under the uniform distribution, and here we replace it with output of some PRG. And for this choice of base error parameter, we obtain that the norm is bounded by alpha, which is equal to 1 over n, for the norm being the standard L1 operator norm. Furthermore, this error term has a nice form. Recall that we can write the mth Richardson polynomial in this way, and we see that the error term from layer I to layer j has the form of the output of the generator from layer I to layer j minus 1, followed by a single truly random step, minus the output of the generator from layer I to layer j. The important observation here is that these entries are weighted PRGs. They're simply the difference of two unweighted PRGs, and so by choosing rho in a fairly natural way, we can encode this as a weighted PRG. Furthermore, the polynomial itself has an even nicer form. if we consider the 0nth block of Lm inverse tilde, we have that it consists of at most 2 to the m times n to the m products of order m approximations, where for a particular term in the sum, we have first a plus minus 1 weight, followed by using the first approximation from layer 0 to layer I2, the second approximation from layer I2 to layer I3, and so on and so forth. This has the form of a weighted PRG. Furthermore, choosing m in relation to our desired accuracy parameter and to our base error, we obtain that the difference between Lm inverse tilde and random walks of length n from layer 0 on the branching program is at most epsilon. And what this means is that the weighted PRG encoded by this entry is an epsilon weighted PRG. Now we might be done. All that remains is to compute the seed length of this weighted PRG. In order to generate an output of this weighted PRG, we need to select a summand and then generate seeds for the approximations in this product. Selecting a summand costs us m log n, which is equal to order log 1 over epsilon, which is fine. But generating the m independent seeds for a product of these PRGs costs us m times log nw, and so is in fact no better than Nissan. So as of now, we've made no progress. Luckily, we can observe that m, which is equal to log base n of 1 over epsilon, is very small, and so we can derandomize these products using existing tools. Rather than drawing order m independent seeds for each PRG, where here we just fix a single product, we can correlate these seeds using the INW generator. For some error parameter, gamma greater than 0, we can derandomize one of these products with seed length s base, where this is the seed length for a single Nissan PRG in the product, plus order log m times log mw over gamma. Here, we can let gen be the weighted PRG, obtained by derandomizing all products in the sum in this way, with error chosen that we survive the union bound over the at most n to the m times 2 to the m different products. Then we have the gen is within epsilon of that particular block of Lm inverse tilde, or the weighted PRG with large seed length. Now we can put it all together. First, we take m to be log base n of 1 over epsilon plus 1, and we obtain that our weighted PRG of large seed length is an epsilon over 2 weighted PRG. Then we apply the inner step in the same manner as before, and we obtain that gen is an epsilon over 2 approximation of our weighted PRG with large seed length. Then we finish by the triangle inequality, and note that the seed length of gen is equal to the seed length required to select a term, plus the seed required to generate the seeds for the product. This is log n to the m plus the base seed length, which is log n times log nw, plus log 1 over epsilon times this error term, which works out to the seed length we obtain for the ordered branching program case. So we've completed the proof of the ordered branching program case, but we still have our further goal. We want to obtain a seed length of log n square root log n over epsilon plus log 1 over epsilon. And here we want to achieve it for unbounded width permutation branching programs. There are 3 limitations of the previous method in our goal to prove the main theorem. First, discussing the first 2 as a group, we needed to take the base error parameter for the Nissan PRGs to be inverse polynomially small in order to make this error matrix have norm less than 1, such that the Richardson iterations converged. Unfortunately, even if we had managed to do something to reduce our requirements such that we could take delta even to be a constant, even a constant error base PRG for ordered branching programs has seed length omega of log squared n. This is due to the log n times log nw terms in the seed length of the Nissan and INW generators. And finally, when we derandomized these products of outputs, we lost a factor of log w in the seed length. Our main result is to evade these barriers for permutation branching programs. First, we use an analysis of the INW generator for permutation branching programs from Pyne Vedant. Second, and this is the most involved part of our construction, we use preconditioning methods from Ahmadinejad, Kellner, Murtaugh, Peebles, Sidford, and Vedant. And third, we use an analysis of the INW generator for high-degree permutation branching programs. Now we'll discuss the first two of these modifications. Recall that in the ordered branching program case, the Nissan and INW PRGs have seed length log squared n even for constant error. Here, we can apply existing results for permutation branching programs. We have that the INW generator epsilon fools PBPs of unbounded width with a single except vertex with seed length essentially log n times log 1 over epsilon. So with no dependence on width, but the same dependence on the error term 1 over epsilon. In fact, just plugging this change into the ordered branching program construction gives a weighted PRG for permutation branching programs with a single except vertex and arbitrary width that has seed length O tilde of log squared n plus log 1 over epsilon. So here, we already obtain a seed length that is independent of width. And in fact, for sufficiently small error, we obtain a weighted PRG that has shorter seed length than any PRG. However, our goal is to achieve little o of log squared n seed length. In the ordered branching program case, we needed to choose the base PRGs to have inverse polynomially small error to obtain that we had conversion iterations. Here, we use machinery of prior work for solving Eulerian systems in small space. Ahmadinejad et al., rather than analyzing the Laplacian of a branching program directly, they analyzed the cycle lift. So given a random walk matrix W, we first take the Kronecker product with a cycle of sufficient length, here 2 to the r for some r to be chosen later, and then we consider L psych the Laplacian of this lift. And what they show, and what we are able to adapt, is that an accurate estimate of L psych inverse for 2 to the r n, so a cycle lift of length n, implies an accurate estimate of the random walk matrix to the nth power, which itself implies an accurate estimate of random walks of length n from layer 0 to layer n. We modify their construction slightly and obtain a result of the following form. For delta greater than 0 and a permutation branching program with cycle lift Laplacian L psych, there's a positive definite matrix F with condition number poly n, and a weak estimate L psych inverse constructed with the INW PRG with error delta, such that the error term, this time of the weak estimate of the cycle lift inverse, has F norm, where this is the matrix norm defined by the positive definite matrix F, bounded by delta times 40 log squared n. What this means is we have convergent iterations, even if we choose the base error delta to be 1 over poly log n. Now we can put it all together. We first take epsilon to be epsilon over n to survive conversion from F norm to the conventional notion of max norm. And then for base error delta, the base INW PRGs have seed length O tilde log n log 1 over delta. The number of Richardson iterations is log n over epsilon divided by log 1 over delta. Then we take gamma to be sufficiently small in the inner derandomization lemma, and this gives us a seed length of the seed required to select a term, m log n, plus the seed length for a base generator, s base, plus the seed length to create a correlated set of outputs of products here. And so finally, we optimize this by taking delta to be approximately 2 to the minus square root log n over epsilon. And note that we do it in this way because here we have delta appearing in the denominator, and here we have delta appearing in the numerator. And so optimizing to make these terms roughly equal, we obtain the desired seed length. To recall, we obtain an epsilon weighted PRG for permutation branching programs of unbounded width with a single except vertex with seed length roughly log n square root log n over epsilon plus log 1 over epsilon. With this, we have a natural computational model where weighted PRGs are unconditionally better than PRGs. Furthermore, we have that there exists an explicit epsilon-weighted PRG for permutation branching programs of width W with an arbitrary set of accept vertices, with seed length log n square root log n over epsilon plus log W over epsilon. And for this, we break the 30-year-old log squared n seed length barrier for permutation branching programs in the polynomial width regime motivated by the de-randomization of space-bounded computation. Thank you.